Okay, hey folks, picking up where we left off, starting the second half of chapter 7. So this is going to be predominantly qualitative, so conceptual, not a whole lot of math. However, these concepts get kind of weird because now we're dealing with the quantum mechanics world. Okay, so I'm going to start by introducing this Heisenberg uncertainty principle, which maybe that's somewhat familiar for you, right? From Breaking Bad, right? The guy's name, he used Heisenberg as the alias. So Heisenberg was a famous quantum mechanicist, and so he said, based on this idea that electrons also act as waves in atoms, there's a fundamental limitation to just how precisely we can know both the position and momentum of an electron at any given time. And there's a famous equation that describes this, and I'll just show it to you just so you can see it. I'm not going to make you do much with this equation. But where is this coming from? Why does he say we can't really know both the position and momentum of an electron at any given time? Well, that comes back to this idea that, remember, we had to adjust the Bohr model, right? So in the Bohr model, it works really well for just hydrogen because we have one electron in each one of those orbits, okay? But as it turns out, when we put more than one electron in these orbits, they interfere with each other, right? Remember when we add waves either constructively or destructively? As it turns out, they interfere with each other, okay? And so these bound electrons, or electrons that are part of an atom, they also have this wave-particle duality, okay? And a result of that ends up being Heisenberg's uncertainty principle. Where now, if I have an electron, let's say I have an electron moving round and round and round a nucleus, okay? So I might know exactly where it is, there it is, but I don't know where it's going, okay? So that's what this equation says. It says if we know its position very precisely, then we don't know where it's going. Or conversely, if I know where that electron is going, I have no idea where it has been. So I'm only talking about this stuff briefly. We could spend an entire semester talking about this stuff. And in fact, that's what I'm going to be doing in the spring, teaching Chem 362 quantum mechanics. So this is really just an introduction, okay? And so now from Heisenberg uncertainty, another famous scientist, Erwin Schrödinger, came along and says, well, because of Heisenberg and the fact that these electrons are behaving as waves, we're going to treat their positions with a probability function. So if we're saying we don't know really where they are, we can say, well, we maybe know most probably where they are, okay? So what we do, we take what's called the wave function psi, that's a Greek letter psi, okay? Oops, I just wrote the letter. I meant to write PSI for psi. Okay, so what Schrödinger does is says, well, there's an equation we could come up with that's going to describe the wave properties of these electrons. We call it the wave function. And when you take the wave function squared, psi squared, versus this distance from the nucleus. So now if, for example, on my picture right here, that spot, that's the nucleus. And if I start drawing an arrow out here, I'll say that's my radius, so that's my distance from the nucleus. Then there's some distribution, okay, some probability distribution that says the most likely value is at the top, most likely or most probable, okay? But these other values, right, they say that there is also some finite possibility of finding the electron, okay? So now what happens is, instead of orbits, okay, like these single two-dimensional orbits, they're really like orbitals, okay? And actually this picture of somebody throwing a rock in a lake right there, I think this is actually a really cool picture of how we can think of these orbitals. So right here in the center, let me change, maybe yellow will show up nicely. Okay, so right here in the center, that would be our nucleus, okay? And so someone drops a rock there in the center, and we see these waves start to propagate out, okay? Like, so maybe there's like a distribution there, right? There's like a probability wave. And then here's another probability wave. And here's another probability wave, okay? So what Schrodinger's wave equation is saying is where there's a large peak, like what we said there, there's a likely place of finding the electron. And when there's a small peak, like I'll point to right here, where this starts to drop towards 0, so it's not very likely to find the electron there. Later on, we will call these nodes. We will learn that nodes are regions where there's no chance in hell you're going to find the electron right there. So no probability of finding it right there, okay? So again, we could spend a whole semester describing this stuff, but this is just an introduction for now. And what all of this stems from is the idea that electrons also have wave-particle duality. So we can't really treat them like these orbits. We have to think of them as these three-dimensional shapes that we call an orbital, all right? And we use a system of numbers to describe those things. And those numbers are called the quantum numbers, okay? So quantum numbers describe the physical properties of an electron within an atom. And these are wave properties, okay? Wave properties mostly. There are some particle properties as well because we recognize electrons have wave-particle duality, okay? So you can also think of quantum numbers as an electron's address on the periodic table, all right? So we're going to put these quantum numbers together and we're going to see how they map out on to the periodic table. And they very much are like an address, okay? So the first one that we start with, number 1, is the principal quantum number. And I've already described this. The principal quantum number, N, is related to those energy levels. So I'm just going to back up really quick. We're going to back all the way through this, right? And so when we were talking about the hydrogen spectrum, okay, all of these different lines, these are all of the energy levels that are related to the principal quantum number. So in some ways, you could kind of think of the principal quantum number as let's say your state. So if, let's say this is the address, we'll call this the state that you live in. So California, for example, okay? And so now we go to the next hierarchy, number 2, the angular momentum quantum number. So this describes the angular momentum of an electron, okay? Oh, and by the way, I didn't say, but principal quantum number, I think, we talked about this earlier, it's just values, integers. 0 doesn't count, so it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, okay? So the angular momentum quantum number, L is the letter, it depends on the principal quantum number, okay? So I really like to think of this as like the city that you live in, for example. If we were thinking of this as a hierarchy for addresses, okay? So the angular momentum quantum number is dependent on the principal quantum number. And so it can take on any value from 0 all the way to n minus 1. So for example, suppose that n equals 2, okay? So then this means L, so we would say therefore L could equal 0 or 1, right? Because 2 minus 1 gives me 1. So this could include all values 0 to 1. So for example, if n was equal to 3, then the angular momentum quantum number could be 0, 1, or 2. So all we're doing is just describing the possibilities. We haven't described an individual electron yet. We're just talking about the possibilities. Okay, then now the next hierarchy, number 3, the magnetic quantum number. So that's an M subscript L, M sub L. And this could really be, you could think of this as the street that you live on. Okay. And so that is based off of quantum number L. So you can see ML can be any value from negative L to L, including 0. So again, if we still had this n is equal to 2, we could have L equal to 0 or 1, okay? And then correspondingly, my ML could be negative 1, 0, or 1. So that includes that 0 right there, okay? And so let's see, instead of using, so we can use numbers for ML, or excuse me, we can use numbers for L, but we could also, I'm saying this all backwards, we can use numbers for L, but more commonly we use letters. So that's where this is at right here, okay? So here you can see our value of L, 0, 1, 2, 3, 4. This is as high as the periodic table goes. So technically the periodic table doesn't go, it really doesn't go past 3, okay? So this number 4 is theoretical for when we find more atoms and the periodic table has to get bigger, okay? So this is where we're at right now. So this is where the periodic table stops currently at L is equal to 3. So what do all these mean? Well, when you have 0, we often use the letter S for 0, okay? We use the letter P for L is equal to 1, D for 2, F for 3, and because that's where the periodic table stops, what people decided the next logical thing to do would be to go in alphabetical order. So G, H, I, J, K, etc. But we're not there yet because technically we only have S, P, D, and F. So these things they actually stand for something. So S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fine. So these are historical names that are based on the spectra, based on the way that the spectra look. So I'm not going to get into a whole lot of detail of why it's sharp, principal, diffuse, and fine, but that's where those letters come from in case you're curious, okay? So 0 for S, 1 for P, 2 for D, 3 for F, you should know that, okay? So now we can also build up this a little bit. And so as it turns out, with the L values, okay, if I also look at the value of ML, which is based off of L, okay, so it can only be 0 when L is 0. And here's how this works. That is 1 ML number, correspondingly 1 orbital per shell. So I'm going to draw an arrow to this thing. And we're seeing actually how these numbers, it's kind of like a computer code. These numbers are not very intuitive. So they really are based off of like a computer code in some ways, okay? So for L is equal to 0, there's only 1 orbital per shell. Well, what's a shell? Well, that thing that I just described. S shell, P shell, D shell, F shell, okay? So just 1 orbital per S shell. Well, what about L is equal to 1? Well, when L is equal to 1, ML can be negative 1, 0, or positive 1. That's 3 ML numbers, and then check it out. 3 orbitals per shell, 3p orbitals per shell from the 3 ML numbers. So now you notice the next one is 5 and then 7. So how do we get 5 and 7? Well, when L is 2, I can go negative 2, negative 1, 0, positive 1, positive 2. Yep, that's 5 ML numbers, 1, 2, 3, 4, 5, correspondingly 5 orbitals per shell. And I'm going to describe where these angular nodes come from in a moment, okay? So we'll get here in a moment where these angular nodes come from. And then finally, you might have guessed this: when L is 3, -3, -2, -1, 0, 1, 2, 3. I know that's hard to read, but that is 7 numbers. 7 ML numbers giving me 7 F orbitals per shell. And I'm going to describe what all of these things mean soon, okay? For now, we're just establishing the rules of these numbers, and I'm going to show you where all of these numbers manifest momentarily, okay? And so there is one last quantum number we need. So if I back up for a second, look, we had the principal quantum number, that's like the state we live in. The angular momentum quantum number, that's like our city. The magnetic quantum number is our street, so what we're missing is like our house number, right? In this analogy, that would be our last thing. So the electron spin quantum number, m sub s, this is like our house number on our street. And as it turns out, in quantum mechanics, there's only 2 allowed house numbers. It's like a mother-in-law unit or whatever. Plus 1/2 or minus 1/2. That's it. And what does that correspond to? Well, it corresponds to the electron spin. So this is actually a particle property of electrons. So I talked about how electrons have wave properties, but they also have particle properties. One of those properties is, as you can see this picture here, electrons spin. And this is what creates what we know as the right-hand rule. And the right-hand rule says, if you take your right hand and stick your thumb up and you make it spin around like this, okay, then you have a magnetic moment pointing up, okay? And so because I only have one right hand, if I want to spin this the opposite way, when it spins the opposite way, I have a magnetic moment pointing down. So these electrons make these little magnets with a north pole and a south pole, just like is shown in this picture. And there's actually some evidence of that, okay? So if we take, for example, so the famous experiment was done with silver ions. So a bunch of silver ions were, I've forgotten the name of the scientist now, shame on me. But these things were shot down a vacuum chamber and passed through, so this is all in vacuum, and passed through a large magnet, okay? And as it turns out, silver plus has one unpaired electron, and we'll see what that means later on. But silver, because of that one unpaired electron, it can actually be spinning up, so it can have a north pole going this way, or it could be spinning down. And as it turns out, there's an equal probability of having both. So what they saw, oh, this was the Stern-Gerlach experiment. I just remembered that. Stern-Gerlach experiment. So what they saw was after they passed this beam of atoms through this magnet, they split. And they saw 2 points on a screen where those atoms were colliding with the screen. And one corresponds to the ms plus 1/2 state, which we call the spin up. And then the others corresponded to the ms negative 1/2 state, what we call the spin down, okay? And so in the silver case, because it had one unpaired electron, there's an equal probability of it being both, and so both spin states is observed, okay? Another way to observe this, although it's very, very difficult, in the spectrum, and here's hydrogen, and we recall hydrogen only has one electron, and because it only has one electron, it could be either spin up or spin down with equal probability. And so if you were to zoom in on these lines, so remember, these are the lines that we would see from the spectrum, from the different energy levels. Then as it turns out, that spin up or spin down can make just a slight, tiny difference in the energy level diagrams. And what it gives you is what we call a doublet. And that doublet corresponds to the fact that one line is spin up and one line is spin down, and they exist with equal probability. Now, as we'll see, when we have atoms with paired electrons, and maybe you have some experience in this from your high school class or another chemistry class, but electrons really like to be paired because when they're paired, you now have North Pole and South Pole and North Pole and South Pole, right? And that's very stable when I can combine the North Pole and the South Pole. And so when you see atoms like that or molecules that have paired electrons, these, a doublet like this or like a result from the Stern-Gerlach, you wouldn't observe that. You would not see that happen, okay? So this is the experimental evidence of these spin numbers, okay? So in summary, we have principal quantum number n. That's the main one. That's where we start, okay? That's why I said it's like our state. We have the angular momentum quantum number. That's like the city we live in. That's based off of the principal quantum number. We have the magnetic quantum number, which is like the street you live on. So of course, that's got to be based on the city you live in. And then finally, we have the electron spin number. That's like your house number on the street that you live on. And there's only two possibilities, plus 1/2 or minus 1/2, okay? So let's see how this manifests. So I'm going to go through this list to see that we understand the rules. And if you want to pause it right here to go through this list yourself, I would recommend that, okay? So I'll start by saying if I have n equals 1, that's the very beginning, okay? I can only have one possibility for L. That's L is equal to 0. And my sub-level, I haven't introduced this yet, but my sub-level I would call 1s, right? Remember, because when L is equal to 0, we call that S. And based off of n, our sub-level designation becomes 1s. And I only have one ML number, 0, that's based off of L. And that means I only have one orbital. And that orbital is called the 1s orbital, okay? So I'll draw an arrow to that and say that's called the 1s orbital. Okay, so now what if I go to level 2? So I've got n is equal to 2. So that means now my possibilities, I could have L is equal to 0, but I could also have L is equal to 1, okay? If it's L is equal to 0, I call this 2s. That's still an ML number of 0, which is one single orbital. And so I only have one 2s orbital, okay? But now what about when I have n is equal to 2 and L is equal to 1? Well, when L is equal to 1, that's called P. So I call that a 2p, okay? And now my ML can be -1, 0, or +1. So that gives me 3 orbitals. And as we shall see, there are 3 2p orbitals. So I'm going to say 3 of them. There are 3 2p orbitals, okay? So let's keep going with this. So now if I have n is equal to 3, I can have L is equal to 0, 1, or 2. If it's 0, that's called 3p. And as you might have get 3s, 3s, that's an ML equal to 0. So of course there's only one 3s orbital. However, when I have 3 and 1, that makes 3p, and there's -1, 0, and +1. So that's now 3 3p orbitals, okay? What about 3 and 2? Well, when L is equal to 2, that's called a d. So now that's 3d, okay? And now my ML values become -2, -1, 0, +1, +2, That's 5 numbers, 5 orbitals, and there are 5 3D orbitals, as we shall see. Okay? And so the last one I'm going to do on this example, when n is equal to 4, we can have 0, 1, 2, and 3. And as you might have guessed, that's going to be 4s, 4p, 4d, and finally 4f. Okay? And I'm not going to write all the ML numbers, but it's the same pattern, right? There's 1 4s orbital, there's 3 4p orbitals, there's 5 4d orbitals, and there's 7 4f orbitals. So I've got all of that summarized right here. Okay? So now, with the last little bit of time in this lecture, I'm going to describe how these numbers make up addresses on the periodic table. Because for now, we haven't identified any of these as an individual electron. Rather, these are just the possibilities. Okay? It's kind of like listing, all of the states and then listing all of the cities in the states and then listing all of the possible streets in the states and then listing all the possible addresses in the states and the cities and the streets. So that's what we've done so far. We've just listed all the possibilities. Okay? So how do we map these onto the periodic table? Well, here's how we do it. Okay? And you need to know this. You need to know how these orbital sublevel designations, so in other words, the 1s, 2s, etc., how they map out onto the table. Okay? So first, let's start by noting that these numbers right here correspond to n, the principal quantum number. And look, 1, 2, 3, 4, 5, 6, 7 is where it stops. 7 is our max for n. And notice that they go across. They make the periods, right? So n is equal to 1 goes all the way across. N is equal to 2 goes all the way across. 3, 4, oh wait, but something funky happens right here. So let's back up and talk about that. And I also want to talk about what we notice here is you can see that there's actually 2 blocks for 1s. Okay? Hydrogen and helium make the weird example because, right, you want helium to be over here, but because it's a noble gas, it appears over there. But we really recognize helium is in the 1s block. And if you now look at the rest of these, look, 2s, 3s, 4s, 5s, 6s, 7s, this makes up our s block. Okay? The s block. So now, and you notice that there's 2. And you'll see why there's 2 in a moment. Okay? So now when we go to the p's, we don't have a 1p, and that's correct. Remember, right, when we started with n is equal to 2, it goes 2s, 2p. We don't have a 1p level. It starts at 2p. And then look, we have 2, 3, 4, 5, 6p, and it stops at 6p. Okay? And you also notice that we have 1, 2, 3, 4, 5, 6 p spaces for the p block. We're going to see why that is in a moment. Okay? And then now you notice here we don't start at 1D or even 2D. We start at 3D, and that's because of the way this level 3 works out, right? 3s, 3p, 3d. And we go 3D, 4D, 5D, 6D, but we stop at 6D. And if we were to count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces on the D block. Okay? And then finally, the lanthanides and the actinides make up the F block. And notice it starts at 4, and we only have 4F and 5F, and that's it. And if we were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spaces on the F block. And I want you to remember these numbers that we came up, right? So we noted that for F, there was 14 spaces. For D, there was 10 spaces. For, oh, and this is a mistake right here, sorry. So 4, 0, 4s, that should be a 1, okay? So we noticed when there was, for P, there's 6 spaces, and for S, there was 2 spaces. So can you see the relationship? So it's times 2. Why is it times 2? Because plus 1/2 or minus 1/2. So there becomes 2 possibilities for each space. And so here is what that looks like. So check it out. So here I've put now finally the addresses. So you've got the full thing. So you've got city, state, street, and house number on this periodic table, right? Awesome. So we can see here, n is equal to 1. So n is equal to 1 only corresponds to these 2. The ml is equal to 0, and it can be ml, so it can be 0 plus 1/2, or it can be 0 minus 1/2. That's where I get 2 spaces. And now when I go down to the next S block, n is equal to 2, I can have 0 plus half or 0 minus 1/2. 0 plus 1/2, 0 minus 1/2. 0 plus 1/2, 0 minus 1/2, etc. That's why we see 2 spaces per S block. Awesome. Okay, well, what about the P? Well, now check it out. It goes -1 plus 1/2, -1 minus 1/2. 0 plus 1/2, 0 minus 1/2. 1 plus 1/2, 1 minus 1/2. So there's my 3 ml numbers, -1, 0, and 1, times 2 for each plus 1/2, minus 1/2, to give me 6 spaces in the P block. And as you can see, so I'm calling them block, but shell is also okay. So block and shell are used interchangeably. So now D, right? This is the last one I'll go through, but you can see -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. It all adds up to 10. And if I were to do this with the F block, that's where we would get the 14 spaces. Okay? So that's where I'm going to end it for this video. So that's basically describing quantum numbers. Okay? So to summarize the learning goals, be familiar with the basic principles of quantum mechanics and how they adjust the Bohr model. So the big deal with this, oops, let me get my highlighter. So what I'm kind of wanting you to know with this is that we adjust the Bohr model. The Bohr model is what describes these orbits, okay? But because electrons have wave-particle duality, those orbits are really better described by orbitals. And we have to use the quantum numbers to describe those orbitals. So that's the next goal. Know the quantum numbers and be able to come up with all 4, N, L, ML, MS, for any given electron, including the shell designation and how they map on the table. So for this, I just showed you how they map on the table. But during discussion, we're going to go through some examples, how we can ID a random electron on the periodic table with its corresponding quantum numbers. Okay, so now you notice there's only 3 more learning goals to go, but these are big ones. So I'm actually anticipating that we'll probably have maybe 1 or maybe 2 more videos, possibly 3 more videos, 1 for each of these learning goals. And I'll try to keep them somewhat short. Okay, folks, I'll see you for the next one.